in a very quiet space. No, don't be sorry. Drink your water, juice.
I'm thirsty.
Drink your water, juice, or whatever it is. Drink your Gatorade, hydrate. Okay. So. That way, right? Well, this is the one that was going in and out the other day, you know. Just don't touch anything. Easier said than done. Oh. Okay, so we're going to justify our answers to these questions. This is going to help us use the definition of rational, and then we'll start doing it in proof. So is 10 over 3 rational? Yes, why?
And then or a real number being no, it isn't an integer.
Yeah, both integers, right? This is real because, this is rational because 10 and 3 are integers and that 3 does not equal 0. Is negative 5 over 39 rational? Is it the ratio of two integers? This is not a hard question. Whitney, I don't want you talking right now anymore about these. Not because you don't know this, Whitney, but because we need somebody else to speak up. Yes, it is. Like Whitney said, you can put that negative on the top, so -5 and 39 are integers, and 39 isn't 0, so this works. Somebody other than Whitney again. Is 0.281 rational?
Yes, because it's 281/1000, and those are both integers and not real.
Thank you, Charlotte.
No problem.
How about 7? Charlotte, you earned yourself a break too. Daniel, you say yes. Why?
It's integer.
Okay, keep going. Rational means I can write it as the ratio of two integers where the bottom one isn't 0.
7/1.
Great. Yep, this is 7/1. So yes, 7 and 1 are both integers, and 1 is not 0. How about 0?
It could be 0.
It sure would be, Charlotte. Yes. All right, do you have any questions about those 5 examples? No? Okay. Let's write our first proof of the day of the test 2 material. Here is our first proof. We're going to prove that every integer is a rational number. We're going to go with calling these every integer, let's call it x, is a rational number. You can read this with as an if-then statement. You would say something like, if x is an integer, then x is also rational. Okay, so our scratch work, if we were going to do any, what do we get to assume? Yeah, we get to assume that x is an integer. And what is it that we want to show? Yeah, which means that, so we want to show that x can be written as an integer over another integer, right? Where this bottom one isn't 0. So that's the goal, is to make this fit that description, that definition of a rational number. Okay. So how might we go about this?
It could be x/1.
Yep. So once you write it as an integer over an integer, you need to justify that that actually is what's happening and that the bottom one is not 0. It's got to fit all of the parts of the definition of being rational. So the proof for this, you're going to say something like, let x be any integer. Notice x equals x/1. Guys, y'all were doing this thing, several of you did this on your test where you started this part, the math part, you just like started it right there without a transitional word. That's a no-no. You're starting a new sentence. It can't be with a symbol. That includes numbers. Those are symbols, yeah. So you have to start with a word. Notice, now, observe, clearly, look, see here. Whatever.
Mayday for that?
Mayday, mayday. Yikes. I'd like something. I don't know. Got to say something. You had some creative transitional things in your, I think I remember looking at them and then going to see whose it was to see. some like old English speak, like whereas, whatever,
Oh, I think I might use nevertheless, however.
However's fine, yeah, no, I like it. Okay, so something like this, notice x equals x over 1, and then we're gonna say clearly x and 1 are integers, and 1 does not equal 0, thus x is rational. Don't forget your box.
Do we do the box?
Huh?
Why do we do the box?
Typesetting to know when your proof's done and you've moved on to something else. Like when people were writing things before, you could like really separate stuff. In typing, you would denote that you were finished. Sort of like why you write a conclusion in your paper, like in a paper, so everybody knows you're actually done. These are bookends. You got to start it and you got to finish it. And everything inside of there should make sense logically. Yeah. Your intro paragraph and your concluding paragraph, I guess. And then the body. Okay. The next one we have is that the sum of two rational numbers is rational. So I would like for somebody else who did not volunteer last time to talk to me about what, I should tell you this. Okay. Whitney, do you mind if I use you as an example?
Oh,
Just a bad answer. Yes or no?
I do not mind.
Okay. So Maddie Parsons, if any of you know her, she did a couple of research projects, actually 3, on discrete mathematics and on what would improve understanding in the course and stuff. And in all of that, it was pretty evident that there is a strong positive correlation between grades and understanding and speaking in class. Whitney, would you like to tell us what you made on your exam? 102. Who do you think speaks the most in our class? Well, me, I also would have made 102. Probably. Whitney does, right? Whitney is ready and willing to talk. She's willing to be wrong. She's often not, but like she's willing to try, right? And so she's thinking. She's not just like writing down what I'm writing down on the board without thinking. Yeah. When you're speaking in class, you are actually thinking rather than just like anybody could sit there and just write down the notes and hand them to you later. That's not the point of being in here, right? The point of being in here is so that you're taking in this information and trying to understand it at the same time, right? So what we're going to do, and this is how this is going to go for the rest of the semester, and I have good evidence to show that this works, and if you want to fight me on it, that's fine, we can. But y'all are going to narrate the proofs to me, and we're going to take turns. Whitney's not going to do it all, and I'm not going to do it all. We're going to take turns. And somebody's going to, each time we write a proof, somebody's going to narrate it for me. I'm going to write down exactly what you say. If you get stuck, I'll help you or your class will help you, yeah? And then you're going to take a picture of it so you can write it down later, and then we're going to move on because you're not going to be trying to write while you're trying to think. Yeah? Good? We're going to talk to each other about this. You're going to do this together with me because that's how you're going to be successful. Okay? Yeah? And it may have worked in every other math class that you could go back later and just stare at what you did and figure out what it was and you didn't have to speak in class. But it won't work in here. Or it'll be a lot bigger struggle. It's not going to work. So we're going to work together and we're going to speak to one another. Yeah? Sound good? Yes? And unfortunately for you, if you don't buy into that, I'm the only person that teaches this class. So good luck. You can't like just put it off and try again next semester because it's just me again, and I'm still going to make you do this. So might as well just go ahead and dig deep. Yeah? Okay. So somebody be in charge of the scratch work here. What do we get to assume?
Assume X and Y are.
So what does that mean? And we can actually give these guys, so we can call this A, B, C, D, where A, B, C, and D are all integers. And what else is true about them?
The B and D don't equal 0.
Good. Uh-huh. What is that we're trying to show?
We're trying to show that A over B plus C over D is a rational number.
Yeah, we're trying to, let's do x plus y equals int over int. Is that cool? Yeah? Okay. Is that hard to see? Do you need to move up? Okay. Okay, what should we do then?
So let X, Y be rational numbers. Let's do that.
You're doing great. Keep going. Don't doubt yourself.
Notice that, we'll notice that A over B is C over D.
Don't do that yet because we haven't defined them. So let's say by definition, x equals,
By definition, X equals A over B. Y equals C over D.
for some integers, A, B, C, and D. And you would say something like with B and D not equal to 0. Cool? All right.
And notice that
Start with x plus y there. Yeah.
X plus Y. Or actually.
Just do the math.
Okay, use A plus B,
hmm
or A over B plus C over D,
hmm
which means, and since B and D are not equal to 0,
We got to actually do it though. So, did I do the common denominator well? Right? Yes? No? So this needs a D, this needs a B. Yeah. So AD plus CB over DB or BD. Yeah. Okay.
you say clearly. Would you do AD plus BC over BD?
AD plus BC and BD are integers. Yeah. What else has to be true for it to be rational? Top and bottom are integers and the bottom's not
Bottom's
0.
equal to 0.
Yep. And so here it's not because B and D aren't 0, so B times D can't be 0. Therefore, we like therefore.
Yes, I was actually going to say that.
X plus Y is rational. We good? That was a good job. Thank you for putting yourself out there first after my big lecture. Okay. Does that fly? Make sense? Not make sense? We good? We understand what's happening? Transitional words and everything, we're good? Any questions that you have?
The only thing I was confused why we, started the proof halfway through the scratch work.
Because Daniel wanted to.
Okay.
And that's fine. Do you know that I often don't start by writing scratch work? I start writing the proof and then I get to a point and I'm like, oh, what did I actually need to do here? And I'll go off to the side and do some like messy work and then go back into the proof. But this, we all think about this differently, right? So if you would like Charlotte to have all of your stuff organized before you jump in and write proof, do that, that's fine. Ruth, that's probably where the camp you're in also, right?
I was very confused. I was like,
We stopped because Daniel was ready to start writing a proof and I wasn't going to stop him. And he did great. And then we got to the point where we needed scratch work, so we went over and did it. It's fine. Yeah?
Whenever I write the proof, I just kind of do it from mindlessly.
Yeah.
Like the notice this part, I just copy over like what I wrote on the other side. I don't even think about it at that point.
Yeah.
It just kind of. just write
I
it
will
in there.
often do a like copy and paste when I'm on my iPad, scratch work into the proof. Because I also am not thinking about it, I'm just copying down what I did in scratch work, yeah. Okay, do we have any questions about this proof? Are we good to move to the next one? I don't know what the next one is. Oh, good. Okay, so you had a good example there for how to do number 3. Who would like to volunteer to do this one? This takes longer, sure, but you learned more, so it's cool.
Call X and Y the product of two fractions of A and B.
Start over. What? Start over,
So-
back up, slow down.
Since prove that the product of two rational numbers is rational,
Okay.
so would you do X times Y?
Okay, so we need 2 rational numbers first, right?
Right.
Okay, so we're gonna let X and Y be rational, yeah?
I would set it the same way we did the last one. And then go.
Sure would be the same setup. So you've got 2 rational numbers now where all 4 pieces are integers and the bottom 2 are not 0. Okay, go for it, Ruth.
And we want to show that X times Y is a rational number. Which is an integer over integer and
Cool.
bottom integer is
Awesome. All right.
So X times Y equals A and B plus times C.
Mm-hmm.
Then we multiply them together, it's AC over B. Done.
Yep, we are. Those things are products of integers, so they're both integers. The bottom 2 pieces couldn't be 0, so when you multiply them together, they're not 0 still. Okay,
And so start the proof.
okay,
So let X and Y be rational numbers.
good. Keep going.
By definition, X equal to A over B. Y equals C over A, B, C are integers.
B or D, right. That one's got a comma. Yep. Okay,
Notice X times Y equals A over B times C over D. Since B times D does not equal 0.
keep going. Since that what? What's the rest of that sentence? What has to be true, Ruth? What are the 2 things that need to be true for this to be rational, which is the thing we're trying to show?
B and D can't equal 0.
BD is not 0, what else? For a number to be rational is the ratio of 2 integers. So we need to know that both the top and the bottom are integers and that the bottom one isn't 0. Yeah,
Okay, so A, B, C, D are integers.
it's specifically here, it's since AC and BD are integers.
And B
Good. So every time we're going for a place where we're trying to make it fit the definition, so we have to make sure that we say it explicitly, right? Like what the actual definition is and why it fits. That is a terrible box. Gosh, I've been watching my daughter color a little too much.
This box thing, like, does it have to be a box? Can it change up the shapes perhaps?
Okay, well, for me, you can change up the shapes just to make me laugh, but when you are writing it for like something else, probably don't do that. Ruth already puts like faces in hers, which I'm cool with. You can write QED. Remember I told you you could write W to the 5th? That's absurd, but you could.
Okay.
Just something to mark that you've done. Textbooks have empty boxes because, you know, ink is expensive.
Man, the tiny little box.
But I promise you that's why it is now. It's just stupid, but whatever, it's fine.
Like, yeah, we phone it.
That's also why they don't bind books anymore and why you have to like have them all as PDF copies, which is super inconvenient for actually doing homework, right? Am I the only, is it because I'm old or is that actually really sucky?
I actually like I actually
You agree
like all
or you
my
don't
books.
agree?
I mean, I don't want the book, but
Yeah, I don't want to carry around a book either. Like, I don't want to carry a book around, but
It's so much easier.
it is difficult to like flip back and forth and I don't know. Can you, when they have the answers, do you just click on them and they're there? So it's easier than flipping to the index, I guess.
Yeah. That's
So you're
trade
actually gonna,
offs.
like put in work to go get the answer, I guess.
Yeah. Yeah, it's true.
How can this textbook and paper figure out?
Yeah.
It's terrible.
I do like, I had a student last semester who, because she was doing her homework on her iPad, she would, instead of copying the questions down, she would screenshot them and then put them like in her homework papers. I was like, yes, because sometimes I question what the actual question is and I don't have a text. I do have a textbook. It's in my office, so I'm at home grading. I'm like, what was the question here? Which is why I make y'all write them down because I don't have a PDF copy of the book.
Oh, we're supposed to write this down.
You should be, yeah. You should be writing the questions down so that you know, I told you guys this. You gotta write the claims down and the questions down so you know what you're answering. And also I know what you're answering. Yeah. I mean, if it's like a super long paragraph of it, don't write that. But you know, the gist, the general gist of what you're supposed to be doing would be good.
I tried like screenshotting it, but this was just not fun.
Yeah, that doesn't look
I
super
did not
good.
like this, especially with my crappy printer. It's like different shades of blue.
It doesn't, you're right, that doesn't look very good.
I was like, I don't know if I want to do this. I'm just gonna pull it up and write down the answer.
That's okay. It's okay. It would be really cool if you just cut them out and taped them to your like lined paper or something. I know, I was just joking. Okay, so 4.4, we move to divisibility. This is like a tricky definition, I guess. The trickiest of definitions because it's different than what we would think about. We're not dividing. Everything is in terms of multiplication still. Because multiplication of integers results in an integer, but division doesn't. So divisibility is about being a multiple, which makes this trippy. I get it. But, so n and d are integers, d is not 0. D divides n if there is an integer k such that n equals d times k. D divides n if it's a multiple of n. Cool?
When it says D divides N, does it mean D divided by N, or does it mean N divided by D?
Correct. It's backwards. Yep. D divides n means that d goes into n evenly, integer wise. Yeah. It means that
Okay,
n
so-
divided by d is an integer.
So it's n divided by d equals k.
Right, but we're not going to talk about it that way. But yes,
So just clarifying.
yes, because this is true. So n divided by d is k.
Okay.
Yeah, it goes into it evenly. It is a multiple. D is a multiple of n. That is written.
Okay.
That is written with the vertical bar, which is super cool because that vertical bar means a bunch of different things in math, so. But here we have, D divides N is written like this. That means that D goes into N, N is the bigger one. That's how I always think about it. D is a factor of N, N is a multiple of D. So it's, this notation is like, would go this way if you were trying to write it how we would normally talk about division. Yeah? Okay. So the definition says D divided N if and only if there exists an integer K, where N equals D times K. So we're going to do proofs with this too, perhaps, obviously. But before we get into that, we're going to determine if these things are true or false. So we get used to using the definition again. This is sort of our method for doing everything. Get used to the definition, then start doing proofs with it. So does 3 divide 12? Yes. Is 12 a multiple of 3? Yes.
Yes.
Yes, 12 is equal to 3 times some integer. That integer is 4. We good?
That's backwards. If it was the other way around, then I just think of it like a fighting.
Yeah, but we're not.
Right.
But we're not doing that. Does 1 divide 16?
Yes.
Yes, so we can write 16 as 1 times an integer. That integer is 16. Does 12 divide 4? No. Here, we can't write 4 as 12 times an integer. Are we tracking? Okay, does 7 divide 7? Yes, 7 is equal to 7 times 1. That thing is an integer, so we're good to go. Does 2 divide 0?
No.
Actually, yes.
Yes.
0 is equal to 2 times 0, and that's an integer, so it's okay. Does negative 16 divide 32? Yes. We can write 32 as negative 16 times 2, and that's an integer. I made this a negative 16. Yeah, sure would be negative 2. Yep. Need both those negatives. Cool. Okay, what do we think so far? Feeling comfortable? Okay.
So the bigger number is always going to be on the right side of the bar.
Correct. Yep.
Or something.
Think about it as D divides into N, right? So yes, D is the smaller one that goes into N evenly. By evenly, I mean without a remainder, as an integer. Stop. I'm going to stop. When I mean divides evenly into it, you know that I mean like without a remainder?
Yeah.
Do you?
Yes.
Okay. It doesn't sound right. Is there a different way to say that I'm supposed to be saying? That's how you say it, right?
Nicely.
Ugh. Y'all, nicely is, objective, right? Subjective? Spectacularly. Okay, so we have this theorem here where A, B, and C are integers, A isn't 0. If A divides B and A divides C, then A divides their sum. Oh, do you want an example? Okay. It's factoring. 2 divides, I don't know, 4, and 2 divides 6. And then 2 is going to divide 10. Another way, like, if you wanted to think about this, no, let's not do that. Never mind. We will prove this in a moment. If A divides B, then A divides B times an integer C, any integer C. If it divides part of a product, then it divides the whole product. And then you want me to do an example for that too? Yeah, sure. 2 divides 2, and 2 will divide 6. I don't know. C is 3 there. This is the integer that it's the multiple of, you know? How does what?
Oh,
If A divides B and B divides C, then A divides C. Okay, we good? 2 divides 4, 4 divides 8, then 2 divides 8.
When you give the example, it makes more sense. At first, like my brain sees all those letters, I'm like, hold on, what is that?
Yeah,
yeah.
that's fair. Well, we're not that comfortable using the definitions like with just letters yet either, so it's weird.
It is so
Yeah.
weird, like the way it's written. I'm trying to teach myself that, no, this is normal. This is
That's
not
the,
weird.
like, all of the other things that we've done are things that you know, and they're not that weird to like look at as like in their formal definitions, but divides is super weird. And it is uncomfortable, but we'll get there. It's, you know, it's been 10 minutes since we've introduced it, so nobody panic yet, right? You've been talking about even and odd since you were like, I don't know, 4. Like, it's fine. You know, those are things that we can accept a whole lot easier in their formal definitions because we have been doing that forever. Okay, so the idea here, we're going to do these proofs. I think, well, you're going to do part 1 on your own. Or do you want me to show you the scratch work for the proof? Okay, I'm going to do it. I, just regular I, the letter I there, this one. The thing we're trying to prove, the claim, is that if A divides B and A divides C, then A will divide B plus C. For you computer science people, the divides thing here means that the remainder in the mod A here is 0. No, that didn't work for anyone. That did help? No, did not help. Okay.
I said it weird, but I know what you're saying.
Okay. I don't speak computer, so, okay.
Close enough.
All right, so what this is scratch work. So A divides B means that B is equal to A times K for some integer K. Remember, the one on the right is the bigger one. A divides into B. And we also have that A divides C. So that means that C is also equal to A times an integer. It's not the same K, don't do that. Call it L, call those K1, K2, whatever you wish. So for A to divide B plus C, what we want to show is that B plus C is equal to A times an integer. That's the definition of divides, yeah? The definition of A dividing B plus C means that that B plus C is some integer multiple of A. So what do you see that we should do to get to that point?
If we set, if it's B plus C, then we could do A times K plus A times L.
And since K plus L is an integer, we're done. Yeah or no? Okay. Okay, so part 2 here of this theorem is that if A divides B, that A divides B times C for any integer C. So we are going to do scratch work and a formal proof here. What do we get to assume? And further that A isn't 0, but yeah. What do we get to assume? Yeah, we get to assume that A divides B, right? And what that means by definition is that B equals A times K for some integer K. What are we trying to show? That A divides BC, right? And what does that actually mean?
BC equals A times something.
Specifically, that something is an integer. Yeah. All right, how are we going to get there? What's AL?
Oh, I set this up differently. I set C to be A times L.
But we don't know that A divides C, so we can't do that.
Okay.
Right, so this is for any integer C, not just for an integer C that A divides into. But if we have this thing, right, we have that B equals A times K, well, then BC equals A times K times C, right? Yeah,
So then
this is A times KC, right, and this thing is an integer, so we're good to go. Right, the divides definition says that if A divides BC, that means that BC is equal to A times an integer. We just found that specific integer to be KC. Specific but arbitrary, right? Yes. What are your thoughts on this?
Where does
Whitney,
C
you're
come
allowed
into
to talk again. You're not still silenced.
play? Where does C come into play?
C is in the claim.
What is, oh, so it's just.
C is just an integer, a random integer. We know nothing about it.
It's just there.
It's just an integer. Okay.
So.
So what?
What did you say, B and A here?
A, B, and C are all integers and A is not 0.
A isn't zero.
Yeah, because the divides thing, A can't be on the bottom, which would be the first thing here. You know.
How do you get from the B equals AK to BC equals AKC?
I am using, this is what I told my class yesterday in my pre-cal class. I'm glad I get to talk about this again. I thought it was a great example. The reason that I write this stuff down all the time, the want to show thing, is because the place where I'm headed is the thing that guides my decisions, right? So I have to know where I'm going to make the right choices to get there. Yeah. So here's my faith integration for the day. We'll just call this biblical integration because I don't know that this is faith, but whatever. So when Peter starts walking on the water, what's happening? He's fine. He's walking on the water. Why? Because he's looking at Jesus. And what happens as soon as he looks down at his feet? he sinks. He's not paying attention to where he's going anymore, or who's allowing him to get there, right? So he loses his way and has no idea what's happening anymore, and he starts to sink, right? But then Jesus saves him when he looks back up at him. This is not Jesus saving you, but this is the idea here is that I'm supposed to be getting the thing I'm trying to reach is where I have BC equals A times an integer. I have B on the side of any equation that's true. So to get BC, I'll just multiply both sides by C and I'm good to go.
Oh.
It's because I'm trying to get this guy, which will hopefully lead to this guy, right? So I'm multiplying that C in. And at some point in algebra, abstract algebra for you, Ruth, you're going to talk about like right multiplication and left multiplication. They're not always the same. So it matters. But in this case, since we're in the integers, we're going to stay in the integers when we multiply here by C. So it's fine to do that. Also because the target is that I would have BC equals A times an integer. And that's what allows me to get that.
Oh, okay.
Okay, so proof is.
A divides B, or yeah.
We're going to let A, B, and C be things first, yeah?
Oh, okay. Yeah, sure. Let A, B, C be integers, and A not equals 0.
Cool. Now I'm ready.
Yeah, assume A divides B, and by definition,
Don't worry about what it is by definition of, but by definition.
By definition,
Mm-hmm.
B equals AK for integer K.
For some integer K,
Notice BC equals AKC, right? And then do maths. Now, KC is an integer. Therefore, what would be just A divided BC equals AKC.
A divided BC, you're done.
Oh, that's just it.
Just it, good, done.
Oh, okay.
What's the assume A divides B? What was that for?
That's the claim.
Okay.
That's the if part. So you assume P and hope that Q follows, yeah? So we assume P and we're going to prove Q.
Okay.
All right. Any questions about II? I have a question for y'all. What'd you say?
Okay.
We're cooking? Good. What's the web assigned homework look like? Is it due tonight?
4.3, 4.4.
There's 2 due tonight. I'm probably gonna push though, so nobody panic about that since we are just now covering them. We're a day behind, remember? Well, we're really 2 days behind, but it's fine. We're on schedule. We're 1 day behind because we moved the test a day. So all of those web assignments are off by a class period. So I'll fix those, but I have a sick kid and a lot of other crap happening. I'm doing my best, but don't panic about those tonight. I will try to remember to go change them in my office in just a moment when we leave here. But I can't make any promises. Okay? But 4.3 and 4.4 won't be due until Thursday night. So that y'all have time and you can ask me questions, before then. Cool? Good. Okay, perfect. Let's do I here. So like I'm a mathematician, so this would never happen. But I don't always do this. I don't just like sit at home thinking about this. I have thought often, and I think a student made me think about it once, so shut up and just tell you. I think about what I would you know how like a baseball player walks up, they have like a walk-up song that they choose, right? I wish that I had like a, when I enter a classroom, I wish I had a walk-in song, you know?
That would be cool. You need to tell us so we can play it when you walk in.
Well,
What song would it be?
What song would it be?
y'all ready for this?
Yeah.
That would get me hyped and like is, you know,
Okay.
it's on the nose, right?
What?
It's like, it makes sense. Are y'all ready for this? It makes sense. And also the beat is good and I would get excited to like be here.
Okay. Thursday. Right.
Don't do it. Don't do it. It make me embarrassed. Okay, so we're proving part I of that proof now. Of that theorem, I mean. The statement is that if A divides B, I'm looking at it, it's on a different page for you. If A divides B and B divides C, this is the transitive property for divides, then A will divide C. Okay, so our scratch work here. What is our ultimate goal? I guess maybe tell me that first. What are we trying to show? Ruth, I want you to do this. What are we trying to show ultimately here?
A divides C.
Cool. Okay, so what does that actually mean?
Basically just kind of like the transitivity.
No, that's the ultimate goal here is the transitive property, but what does it mean for A to divide C? That alone, what does that mean? Because we don't know, that bar makes no sense to us for like what we're actually doing, what we're actually going to be doing. What is it that we're going to show? Yep, that C equals A times an integer. We don't know what that integer is, we're gonna find it. That's the definition of divides. Go back to, I don't know, whatever the heck page it was. Page 3. Okay, so that's how we actually like use it in practice in proofs. What do we get to assume? Ruth, you want to take it or you want to let Whitney keep doing it? What does that mean? What does it mean for A to divide B? Look at the definition of divides. Go back to page 3. Look at that definition. What does that mean? No, you're looking too far down. Go back up to page 3, in the middle of page 3. The definition part. What does it mean for A to divide B?
A is a factor of
What does it mean, like symbolically? Which one's bigger, A or B?
B is
Okay, so B equals A times L. Go with that. I should use a K first, shouldn't I? Okay, what does it mean for B to divide C? Which one's bigger?
C is bigger.
So C equals B times L. And K and L here are integers. Cool? All right. What are we trying to get to again?
But C is equal to.
Okay, so right now I have C equals B times L. What do I do with that? I also have B, Whitney. What does B equal?
done. Oh, have we replaced?
Mhm. So to do the proof, we're gonna let A, B, and C be integers and A is not 0. Okay. What do we want to do from here?
By definition,
Nope, not yet.
Is B also empty?
Oh, yep. Sorry, thank you.
but A equal B equal AK and C equal BI.
Can't do that yet. Okay, what do we get to assume, Charlotte?
A divides B and B divides C.
The P part of the thing we're trying to prove, right? Assume A divides B and B divides C. Then by definition, B equals A times K and C equals B times L for some integers K and L.
So this equals AK.
Not helpful. I mean, it does, but that's not helpful.
C equals BL.
Oh. Since KL is an integer, then basically dumb. Shame. A divides B and B divides C.
That's what we assumed.
no.
What did we actually show?
That A divides C.
How are we doing? We good? Yes? Okay. Ruth, did you get that? Did you take a picture of that? Ruth, okay. Okay. So next up, we get to talk about prime numbers again. An integer p greater than 1 is prime if the only positive factors of p are 1 and p. That's a whole lot better said than the last time we did that definition. But because we have divides now, we can do this with divides, which is kind of fun. An integer is composite if there exists an integer a that divides n, and a is between 1 and n. Yeah? That means it has a factor that's not 1 or itself. Cool, yeah? Right. So then we have the fundamental theorem of arithmetic. It says that every integer greater than 1 can be written uniquely as a product of powers of primes in increasing order. This is just that you can factor everything down to primes, yeah? Okay, so 2 is 2 to the first, 3 is 3 to the first, 4 is 2 squared, 5 is 5 to the first. This is how this works. This is going to come back later, but this is a fun little exercise now. 7 is 7 to the first, 8 is 2 to the third, 9 is 3 squared. 10 is 2 to the first times 5 to the first. 11 is prime, so it's just 11 to the first. 12 is 2 squared times 3 to the first. what this is really going to give us is that if a number divides like 6, then, and it's prime, the number, then it either divides 2 or it divides 3. Yeah.
Why would it be like 2 to the, 2 squared times 3 to the first instead of just 12 to the first?
Because 12's not prime. You want to go to prime factors. So 2 and 3 are
Oh, I
prime.
see.
Basically like reducing it.
Yeah. Reducing it to like its factor tree, you're just writing down the very bottom thing.
Okay.
Yeah. But again, this is going to help us because if we know that, like, I don't know, something divides 8 and it's smaller than 8, then it divides 2. Like the idea is that okay, that's a bad example because it's 2 cubed.
So like using the smallest possible numbers.
Right, like if we know a thing is prime and it divides this product of things, it's got to divide one of the factors, and that is going to be useful for us later. Yeah. Or some combination of the factors. You're going to do this on your homework, I think, with like 12 and 25 or something. It's like 25A and 12B or something. And what's going to happen is, like, if 25A divides 12B, does that mean that A divides B? And the answer is yes, because this is 5 squared times A, and this is, 2 squared times 3 to the first times B. So if there is division that's happening, if divides is happening here and it works, it's got to be between these two things because of the fact that 5 and 2 and 3 don't go together as products. Okay. I think that's on this homework, the written homework. Okay. Another big theorem. The quotient remainder theorem. This one is also trippy, so let's dig in on that today, I guess. So the quotient remainder theorem, and then we're going to do our first proof, another proof method. So we have direct proof, which is assume the P part show the Q part. Yes? Right, that's the only kinds of proofs we've been writing, or counterexamples. But proofs we've been writing have been assume the P part show the Q part follows. Yes? So we're going to start adding methods of proof to that. Proof by cases is one of them. That will happen here. We're not going to get to that today, so don't panic. For this one, we have an integer n and a positive integer d. Then there are unique integers q and r. R is between 0 and d, such that n equals d times q plus r. This is dividend, quotient, and remainder. That's what those letters are for. If d divides n, what's r? R0, yeah. If d divides n, then n equals d times some integer q, right? Okay, whatever. Yeah?
Yeah, I got it.
Okay. That would mean that, like, n, d divides n means that n equals d times some integer, right? And then that you have this plus a 0 remainder. So n is the dividend, d is the divisor, q is the quotient, r is the remainder. This is trippy. Notice here the thing that's happening too is that this divisor and r have these bounds that are involved. So r has to be between 0 inclusive, because if it divides evenly, the remainder would be 0. But r can't be bigger than the divisor, obviously, or the divisor would grow by 1. Does that make sense? So this restriction is going to help us in a little while prove that every number is either even or odd. Because that remainder is going to have to be 1 or 0, which makes it even or odd. Amazing. Okay, so this is just a rewritten form of normal division. It's uncomfortable, but it works. Call this one an N instead of an A, and then it will be clearer what's happening. So N divided by the divisor is the quotient plus the remainder over the divisor, right? This is the thing you've been doing forever. R is the remainder when N is divided by D. Okay, so what we're going to do right now is look at these guys. We're going to write them with the quotient remainder theorem. This is also called the division algorithm, which is fun. Y'all like algorithms? Not you, Sky. Everybody else, not you, Ruth. Everybody else likes an algorithm. No? Whatever. Okay, so we're gonna do that 52 divided by 8. So we have 52 is equal to some number times 8 plus a remainder. Mm-hmm. Plus 4.
Well, you're forgetting ones.
Maybe I should write those in the other order. Maybe that would be better. Okay, negative 26 divided by 3. So we have negative 26 is our N. 3 is our divisor. We need a quotient and a remainder.
-7.
So if you use negative 8, that's negative 24. Then you got to subtract 2. What has to happen to that remainder? What's that remainder's restriction? Yeah, right. It's between 0 and your divisor. So this R value that we're going to use needs to be between 0 and 3. It could be 0. It's not, but it could be. So instead of negative 8, go to negative 9 so that then you can add stuff. Yeah. Yeah. Here, let me do this with mod stuff. This will make it better. This is the case where mod, like arithmetic, modular arithmetic matters. Oh, look, we're about to talk about it. Good. This because on this one, like when you have the remainder mod 3, it's going to be 0, 1, or 2, right? And that's what this is allowed to be, 0, 1, or 2. That's all.
What happened to the 4 up there?
Huh? This 4 is allowed to be 4 because it's between 0 and 6. Whatever the divisor is your upper bound on your remainder. Your lower bound all the time is 0. So your remainders, this is a thing that you know, y'all. Let's look at, do a thing like 35 is the example I have written down. 35 is 4 times 8 plus 3. Right, 32 plus 3, we have it. If my divisor here, I made that to be 4. So this R value has to be between 0 and 4. It is 3. If I went to 36, then that divides evenly by 4, I mean. Yeah. Right, yeah. Mm-hmm. This would work either way if it was 6 or 8, but yeah.
Well, I guess if you're given the 8.
Yeah, right. The 8 is written as the divisor here, but you could write that divisor as 6 and it doesn't change the unique setup there.
Does it work with the negative number and see?
Yeah, So for C, the divisor itself is positive,
Okay, advisors cannot be negative.
right?
Okay.
Yeah, if you read back way up here, it does say that. We didn't focus on it because it was before we actually knew anything, but D is a positive integer, positive divisor. Here, like what I was saying, with the mod stuff, negative 26 is equivalent to negative 26 mod 3 is 1, not negative 2, right? Your remainders under mod 3 can only be 0, 1, or 2. Yeah. Did you do mod stuff yet? No. Okay, well, I shouldn't use that as an example then.
Oh, you mean like coding?
Yes.
Yeah. Yeah. It's just-
Oh, I remember that.
Well, I guess what I'm thinking of is, since it's multiplication and like the 8 and the 6 interchangeable.
Yeah, right.
Is there a situation where it's greater than 6, less than 8, or does it have to be less than both generally? Or I don't know why that just came up.
It broke mine the way that you asked it, or something. Like in this case, it wouldn't work for the quotient and the divisor there because the quotient part is negative, right? So this,
It's disqualified basically.
correct, yeah.
Okay.
Otherwise, you can interchange them because it's multiplication, yeah.
Okay, so if there was a situation with the 8 and the 6 where the remainder was 7, it's possible, because we'd be looking to the 6, not the 8.
In theory, yes, but,
Practicality, probably not.
right.
Okay.
Yeah, the divisor does bound your remainder.
I guess
So-
in that case, it could just be written. Never mind.
Okay, well. That's all I have for you today. My time is up. I can't finish those last 2 examples, even though I really want to. It's fine, it's fine. It's 3:20, you're good to go. Have a great day.
Spoiler alert, please.
Yeah. 79 divided by 5 is 79 equals 5 times a thing plus a remainder. This remainder is going to be less than or equal to 5, between 0 and 5. Yeah, not equal to, less than 5.
Would it be?
5 times 15 is what? 75? And so we need 4 more? Yeah? 789 is big. Bye, Marina.
34 plus.
Cool. Y'all have a good rest of your day. I'll see you on Thursday.
Oh my gosh, why is it?
Oh, I have these homeworks that y'all turned in.
Are some of those the ones you just took back?
You don't want it. Okay. Yep. Wait, Logan, take these. Here's yours. Take these. You don't want them either?
Not really.
Jalen, you want yours? You're good, you're good. Come on in. We're done. Yeah.
My son is, got accepted, and he starts in, August.
Okay.
Fall year.
Okay.
Pastor, John.
Yeah.
And, his counselor, Bailey.
Uh-huh.
Sent us over here to see if, we can get any information about anybody who can help him with the math section. He has to take the ACT this Saturday,
Oh, okay.
and so he's having trouble with the math.
Let me grab a student.
Thank you. You want me to tell him to walk in? Because he's just standing out there. He's so
The
nervous.
student might also be standing out there.
And everything. Yeah.
Pastor John said if somebody found someone that does it on the side, that he would pay for the tutoring for us.
Oh my gosh, that's so
I
nice.
know, we just don't know how to find nobody.
Yeah, I
So,
have a student who does the
Okay.
tutoring and I will, I just
Thank you
told him
so
to come over
much.
here. So we'll
Thank you
see.
so much.
Yeah.
His name-
I also,